exactly what we thought it would be the analytical solution, but we can also solve a differential equation using Euler's methods. Volume, all right, so we're ready to go. So now if we have to apply this to a not so simple problem like a pendulum or some other mechanical system, we need to figure out how we can apply Euler's method or any other method to solve differential equations using real systems besides these really simple systems like we did last time. So when we have a real mechanical system like this, we need to be able to get the equation of motion for our mechanical system. And if we get an equation of motion, we're going to get that from our free body diagram. So if I were to draw a free body diagram of my pendulum system, and I were to figure out sum of forces is equal to mass times acceleration, I would get my equation of motion let's see, we're talking about angular coordinates here. So m alpha is equal to minus mg over L, which is the length of my pendulum, times sine of theta, which is the angle of my pendulum relative to vertical. And I'm going to say that my length of my pendulum is 2 meters, and my mass, my pendulum ends up canceling out, so that really doesn't matter. So this equation kind of boils down to the acceleration, angular acceleration is equal to g divided by L times sine of theta. So this is my equation number 2 on my handout there. So we have an equation for the angular acceleration. So if I want to get the angular position and the angular velocity, what do I have to do to this equation? Integrate, right? So if I integrate one time, I'm going to get velocity, angular velocity. If I integrate 2 times, I'm going to get angular position, right? So this is what we call a second order ordinary differential equation because it's the second time derivative of position. So if I were to kind of note that, I might say, d squared theta dt squared. So that kind of reminds me that angular acceleration is the second time derivative of my angular position, or my theta value. So this is what we call a second order ordinary differential equation. So in order to integrate second order ordinary differential equations, kind of poses a problem because all the methods that we have for integrating ordinary differential equations only work with first order systems. So we did a first order system last time, super simple, but now we're kind of stuck because we've got this second order differential equation. So if we want to integrate a second order ordinary differential equation, we actually need to break it up and kind of transform it into 2 first order equivalent ordinary differential equations. So we're going to build up a system of 2 first order ordinary differential equations that will be equivalent to our 1 second order differential equation. So we need to convert the second order ODE into 2 first order. So what do we know about the time derivative of position? So d theta dt is what quantity? Omega, or angular velocity, right? So I can write that equation. I could say d theta dt is equal to omega, or my angular velocity, and that is what order of differential equation? First order. So that's one equation. So that's one first order equation that I have. So that's going to be what we're going to call equation number 3 on our handout there. So the first derivative, and then I could do the same thing. So I got the first derivative of position. What if I also take the first derivative of my angular velocity with respect to time? that's going to be what? Alpha, or my angular acceleration, which I already got over here. So I can now plug that in. I could say my first derivative of omega with respect to time is g divided by L times sine of theta. So now I have two first order differential equations. I have the first one, which is the derivative of position with respect to time, and then I have another equation, which is the derivative of angular velocity with respect to time. Both of these are first order equations. They're equivalent to my second order differential equation over here. That's the second derivative of position. So it's just kind of a way of rearranging my equations so that I now have two first order ordinary differential equations. So anytime we have a higher order ordinary differential equation, we've got to break it down into the equivalent kind of first order system. So if I had a third order differential equation, I need to break it down into three first order differential equations. So you always have to break them down and get them kind of in this simple form, simple as possible, to be able to use them in these kind of differential equation solvers. So any questions about that? Okay, so now if we're going to apply our Euler's method to be able to solve this system of differential equations, we have our generic formula for the Euler's method. We said y at the next point, so I plus 1, is equal to y at the current point, I, plus f of t sub I, y sub I, multiplied by h. So when I apply my Euler's method to be able to solve my system of ordinary differential equations, I just apply it to each equation one at a time. So I start with my first equation, equation number 3 here, my derivative of theta with respect to time, and I start plugging that in and kind of using that in my Euler's method. So if I take equation number 3 and I want to solve that in terms of my Euler's method, if I take the integral of this equation, what quantity am I going to get? So if I take the integral of this equation, what am I going to get as a result of that?
Squared over 2.
What'd you say?
Omega t plus c.
Right, so I'm going to get some sort of theta, well, and then that's going to be my position. My position is a function of time. So my position, theta, as a function of time, is going to be equal to the integral of the right-hand side. If I take the integral of this equation, I'm going to get omega, my angular velocity, is equal to the integral of negative g over L times sine theta dt. Thankfully, because I'm going to do this with the Euler's method, I don't have to solve these integrals. I don't have to figure out what the right-hand side is equal to. But I know that my left-hand side is going to be the quantity I'm trying to look for with my Euler's method. So if I transfer that over here, I'm going to be able to solve for theta at the next step. I plus 1 is equal to theta sub I plus something, and I'll leave this blank, times h, which is my step size, or my kind of my interval I want to solve that integral over. So what did we plug in for this f kind of function when we did the simple problem there? What did we use to solve for that? Right, we used our dy dt. So in this case, I'm going to use my d theta dt, which is equal to omega. So all I have to plug in here is omega, and that's going to be omega at the current time point I. So now if I want to do the same thing for equation number 4, I want to apply my Euler's method to equation number 4. What's the first thing I'm going to write here? What variable is going to be on the left-hand side of my equation? Yep, omega at the next step, so I plus 1 is equal to the previous omega, or the current omega at the current step, plus something times my h. And what goes in here now
negative G over L sine theta.
Yep. Negative G over L sine theta. And because we've got theta as a vector, that's going to be theta sub I, the current theta value. So now I've got these two equations as my Euler's method, and I can basically just plug that into my MATLAB code, my for loops for my MATLAB code that we wrote, kind of figured out last time. All right? So any questions about how we got to here? Okay, so let's quickly see if we can write our MATLAB code to solve this system of ordinary differential equations. So I'm going to open up a new script. And I'm going to do my housekeeping tasks up here at the top. And then when we wrote our script last time, we had to kind of set some things up before we got into our for loop for our Euler's method. So we had to establish the step size, which is h. And do we want to pick a big H, big value for H, or a little value for H? Small value. So the smaller the value, the kind of the more accurate that my differential equation is going to be. So let's pick 0.001, see what that looks like. So when we're doing the Euler's method, we need to integrate our equations of motion over a time frame. So we need to be able to pick what that initial and final time frame is. So let's say we're going to integrate our pendulum over a period of 6 seconds. So we're going to start our t, we're going to get a time vector, we're going to start at 0, finish at 6, and we want to increment by what value? H. So we say 0, colon, H, colon, 6, so that's going to allow us to integrate over 6 seconds. And then before we get into our Euler's method, what other information do we need to establish? The initial conditions. So we need to pick some initial conditions. And because we have two differential equations here, we need to have two initial conditions. We need to have an initial condition for theta. We need to have an initial condition for omega. So I'm going to say that my initial condition for theta, I'm going to call this theta Euler, is going to be pi over 3. And I'm going to put that in the first row, first column of my theta vector. Just go ahead and populate that. I'm going to say that that's going to be pi over 3. So we're going to deal with thetas and omegas and radians per second, so we don't have to worry about degrees. And then I'm going to pick my initial omega. So omega Euler 1, 1 is going to be equal to 0. I'm going to say start with no initial angular velocity. And then there's a couple other things because we got some physical parameters for this problem. So we need to establish what the length of the pendulum L is and what G is, our acceleration due to gravity. So we're going to define those parameters here. So we'll say L is equal to 2 and my G is equal to 9.81. And now I'm going to write my for loop. So I have for I equals to 1 to what? It's going to be my last value of my for loop that I want to put in here. Length of t minus 1. And why do we do t minus 1? Why not just length of t? Right, because we're looking forward in time. We're looking to get the next value, I plus 1. So we can't go all the way to the end because we're going to run out of stuff. So now inside this equation, or inside this for loop, what do I have to put? What should I write here? Our Euler's equation, and then something else. So we'll start off with these two Euler's equations. So we'll start off with theta Euler, and we want to make theta Euler a vector, so we're going to start with one row and then our I plus one column. So that's our new value of theta is equal to the previous value of theta, so theta Euler 1 comma I plus my what? My omega sub I. So that's my omega Euler I, or 1 comma I, multiplied by h, which is my step size. Then inside the very same for loop, I want to put my second Euler equation because I want to solve these all at the same time. So I'm going to put them both in the same for loop. So I'm going to say omega Euler, same kind of format, 1 comma I plus 1. Oops. Is equal to omega Euler 1 comma I plus my d omega dt equation, or my minus g divided by L times sine of my theta Euler. And that's going to be the current value, so 1 comma I times h, my step size. So do we need anything else inside of our for loop? Yes, no, maybe? No, we're good. So we can end that. And then if we wanted to, we could create some plots. So let's do real quick a subplot with 2 rows, 1 column, so that we can plot t, or time, on my x-axis, theta Euler, or my angular position on the y-axis, and then in my second subplot, 2 comma 1 comma 2, I'm going to plot my t on my x-axis and my omega Euler, my angular velocity, on my y-axis. So now we can just kind of get a visual representation of what these quantities look like over our whole pendulum, our time duration that we integrated our pendulum over. So if we save this, I'm going to call mine pendulum Euler, and then we go to run it. Hopefully we get something like this. How do we do? Okay. Let's see. I'll kind of move this out of the way so that people can see everything. Any questions about that? Okay, so now what I want you guys to do is work on your in-class exercise. So that's on the last page of the handout. So your in-class exercise is related to, or is to simulate the motion of a pumpkin coming out of a pumpkin cannon. People actually do this, and the videos are pretty funny if you haven't seen them. So what we're going to do is we're going to simulate the motion of the pumpkin flying through the air. You're going to need to do a couple things. So I provided you a couple kind of hints on some equations that you might need that are going to be relevant. I've decided to kind of scale this back a little bit. So in the description of the problem, on the top there, I said the second sentence says your code needs to determine the angle, blah, 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 blah. I'm not worried about that, so you can eliminate that part from the problem. So the second sentence you can get rid of. Also, the last part of the last sentence in that first paragraph, where it says, and should have a means of determining if the pumpkin has hit the ground or not. You can get rid of that part as well. We're just going to integrate our equations over a fixed time interval that will get us to the ground, and we'll kind of scale this back a little bit. So what you're going to have to do is you're going to have to think about your equations, so draw a free body diagram, figure out the equations that you're going to be using to simulate the motion of your pumpkin. You're going to need to simulate and kind of estimate the motion in both the vertical and the horizontal directions. So you're going to need to look at both of those kind of sum of forces equations. You got to account for drag on the pumpkin, and you got to account for the weight of the pumpkin. So those should be the only two forces that are acting on your pumpkin. Things that are going to be, another two pieces of information that I didn't provide you that will be helpful. Your initial launch angle of your pumpkin should be 60 degrees. I'll write this to. And then we're going to integrate over 9 seconds. That should get your pumpkin to hit the ground. And then if you properly integrate the equation of motion for your pumpkin, you should get that at 9 seconds, the final position. I've got extras somewhere, but I gotta have to dig through my stuff. Should be about 115 meters. Approximately equal to 115. So I will leave you with that. I will say that the process of going through and kind of deriving your equations of motion and simulating the motion of the pumpkin is very similar to the first things you're going to have to do in your final project. So I highly suggest that you figure this out and then move on to the final project. So, I think it'll be much easier to kind of understand this, then move on to the final project and try to jump into that first. So that's what I would highly suggest. All right.